Hello again. In this section, we're going to look at limits involving infinity. So we can have situations where, for certain inputs, as we approach the input, the output becomes very large, grows without bound. And we can describe those limits in terms of infinity. And also we can have situations where the input becomes very large. And then we need ways to describe the output. Both of these situations are limits involving infinity. So let's take a look at them. All right, so first, if we think back to a previous section, I think in the introduction to limits topic, we said that the limit as x approaches 0 of 1 over x squared does not exist. And I wanted to revisit that problem. I said I was going to revisit it and that we would adjust our understanding a little bit. So now let's do that. So as x approaches 0 from the left, as we approach 0 from the left, and here I have a graph of the function. This is the function 1 over x squared. As x approaches 0 from the left, we see the output growing without bound in the positive y direction. Similarly, as we approach 0 from the right, the value, again, becomes very large. It grows without bound, again in the positive direction. So what we will say here is that, yes, the limit does not exist, but it's a different situation than if we had a left limit and a right limit hitting different values. The limits are hitting the same value. It's just that that value is not a real number. And so in this situation, what we'll say is, and the notation we will use is, we would say that the limit as x approaches 0 of 1 over x squared is equal to infinity. So that's what we're going to say for this situation. Now, I understand this to mean two things. Yes, the limit does not exist as a real number, right? The limit does not exist as a real number, because infinity is not a number, okay? It's a concept. The limit does not exist as a real number. The limit grows without bound in the positive direction. If the limit had been growing without bound in the negative direction, then I could say that the limit was negative infinity. But I'll say that this limit, as x approaches 0, 1 over x squared, is infinity. Now, here I used graphical evidence, but there's also a way we can analyze this through understanding what happens as when we're dividing by a number that's close to 0. Okay, so let's see the situation. So here we have the limit as x approaches 4 from the left-hand side of 7 over x minus 4. Let's understand this. Let's parse this a little bit. If we have x approaching 4 from the left, that means that x is less than 4 and near 4. X is less than 4 and near 4. So if we're thinking of our number line, right? There's our number line and here's 4. And we're talking about a number that's 3.9999, etc., right? That's a number that's less than 4 and near 4. Okay, so what happens here? If I take the denominator, if I take x minus 4 and I try to substitute a number that is less than 4 and near 4, what happens to this x minus 4? It gets close to 0, but on what side of 0? X minus 4 would get close to 0 on the negative side if x is less than 4, and we're limiting to 4. So what happens here is this becomes 7 divided by a small negative number. And what happens if we take a regular number, think of 7 as a regular number. If I take a number, a real number, and I divide by a small negative number, well, I have a positive number divided by a negative number, so that would certainly be negative. But what happens if I take 7 and divide it by a small number? Well, if you've done any arithmetic and if you've seen some examples, you should know that if I divide by small numbers, numbers close to 0, the output becomes very large. And so if the output is very large, we can use an infinite symbol. And so this limit, the limit with x approaching 4 from the left of 7 over x minus 4, is 7 over a small negative number, which we'll represent as negative infinity. Now, if we have the limit with x approaching 4 from the right, so now x is greater than 4 and near 4. And so if we were to, again, think of this on our number line, now we're approaching 4 from the right, and we might have a number like 4.00001, maybe. That might be our numerical idea. And so now if I was to take that number and subtract 4 point, a whole bunch of zeros and a 1 at the end, and subtract 4, now in the denominator, I would have a small positive number. And so now I have a positive divided by a positive, which is positive, and 7 divided by a small number, this goes to positive infinity. So then what would we say here? Now that we know the left limit and the right limit, what is the limit with x approaching 4 of 7 over x minus 4? Just as before, since the left limit and the right limit are not the same, we would say that this limit does not exist. Now, what happens in the graph of the function at x equals 4? Well, if you remember some stuff from algebra, you should say, well, I think there's a vertical asymptote at x equals 4. And that would be correct. But our understanding now from calculus and this limit idea says that there's even more information. We know that at x equals 4, so let's just put 4 here on the number line. At x equals 4, if I'm to the left of 4, if I'm to the left of 4, the output approaches negative infinity. So yes, there's a vertical asymptote, and it's in the negative direction over here on the left. However, on the right, the limit is at positive infinity, and so I should have something like this on the right. And there's more to the graph than that, but near x equals 4, that is the characteristics of the asymptote. That's the description of the curve near x equals 4. And we can easily verify this with a graphing calculator. Let me bring up Desmos real quick. And there's the graph of the function. And what I can see here is that near x equals 4 on the left, I see the curve going to negative infinity. And near x equals 4 on the right, I see the curve going to positive infinity. And so that verifies what I saw analytically. So let's get some more practice with this. So here, we're asked to describe the behavior of the function 6x over x squared plus 4x minus 12 at its vertical asymptotes. All right, so let's first identify its vertical asymptotes by using a little bit of algebra. So notice that the function can be written as 6x over, let's see, this would be x plus 6 by x minus 2, using some factoring. And what I see from this is that since there's no common factor between the numerator and denominator, I expect vertical asymptotes at x equals negative 6 and at x equals 2. So now, let's describe the behavior near those. All right, so let's find the limit with x approaching negative 6 on the left of the function, the limit with x approaching negative 6 on the right of the function, the limit with x approaching 2 on the left of the function, and finally the limit with x approaching 2 on the right of the function. All right, and so I'm going to use the same sort of ideas here as I did in the previous slide. If I'm approaching negative 6 on the left, so this means that x is some number less than negative 6. So then what would happen? I'd have in the numerator, I'd have 6 times a negative number, right? Because x is less than negative 6. So this would be a negative number in the numerator. In the denominator, the x plus 6, if x is less than negative 6, then negative 6, a number slightly less than negative 6 plus 6, this would give me a small negative number. And then finally, a number less than negative 6 minus 2, this would just give me a negative number. So in the denominator, in the numerator I have a negative number. In the denominator I have a positive number, because a negative times a negative is positive. So I have a negative divided by a positive, and this would be negative, and I'm dividing by a small number in the denominator, and so I would have negative infinity. So as x approaches negative 6 on the left, that would give me a negative infinity. Why don't you try to complete the rest, these 3 remaining pieces of this exercise now? So it would be a good time to pause. If x is approaching negative 6 on the right, so now that means now we have x is slightly greater than negative 6. It's still a negative number. If it's just a little bit greater than 6, it's still a negative number, our x value, so I still have 6 times a negative number in the numerator. Now in the denominator, I have a number greater than negative 6, and I'm adding 6. So a number slightly greater than 6 plus 6, this would be a small positive number. And a number slightly greater than negative 6, subtracting 2, this would still be a negative number in this factor. So let's see, I have a negative divided by a negative, which is positive. I'm again dividing by a small number, positive infinity. If x is approaching 2 from the left, now again, that means that x is less than 2. Okay, but just slightly less than 2. So I have 6 times a positive number. That would be positive in the numerator. A number that's slightly less than 2 plus 6 would be positive. A number slightly less than 2 subtract 2 would give me a small negative number. So I have positive over a negative, positive over a small negative, negative infinity. And finally, the limit with x approaching 2 from the right of the function. So here we have x is greater than 2, just slightly greater than 2. This would still give us a positive number in the numerator. In the first factor in the denominator, I'd have a positive. And for the second factor, I'd have a small positive. And so this would go to positive infinity. And so here's the behavior of this function near the asymptotes. And again, if I was to get, just a kind of a rough sketch, a rough idea of what's happening here, what I see now is that at -6, I expect a vertical asymptote at -6. And on the left-hand side, it goes to negative infinity. On the right-hand side, positive infinity. And similar behavior at x equals 2. On the left-hand side, negative infinity. On the right-hand side, positive infinity. And I could verify this again with a graph if I wanted to. So here's another function. The function is x minus 5 over 3x squared minus 12x plus 12. And so what I would recommend you do is to pause and try this exercise out on your own. Describe the behavior at its vertical asymptotes by using limits. All right, so the function can be written, leave the numerator alone as x minus 5. And let's see, that's 3 by x squared minus 4x plus 4. And that denominator factors further. That's x minus 5 over 3 by x minus 2 squared. All right, that's a perfect square trinomial factoring as x minus 2 squared. So there's only one value of concern. The concerning value is that x equals 2. I expect a vertical asymptote at x equals 2. Let's see what happens at that. Let's find the limit with x approaching 2 from the left of the function, and the limit with x approaching 2 from the right of the function. All right, so substituting a number that's slightly less than 2, right? If x is approaching 2 from the right, that means x is less than 2. Then I'd have a number near 2 subtracting 5. That would give me a negative number in the numerator. I have 3, which is a positive number. And then I have a number less than 2 subtracting 2 and squaring. This is going to give me a small negative number squared. Okay, so now let's think about this. If I square a small negative number, if I square a negative number, it becomes positive, doesn't it? So this ends up being a negative number over a positive times a, and then if you square a small number, it gets even smaller, right? I know that seems counterintuitive, but let's take a quick example. A relatively small number, 1/10. If I square it, I get 1/100th, don't I? That's an even smaller number, right? So if I take a small number and I square it, I get an even smaller number. Now remember, by small we mean close to 0. All right, so what happens here? If I take this small negative number and I square it, I end up with a small positive number here. And so I have a negative divided by a small positive. That will go to negative infinity. Similarly, if we have x approaching 2 from the right, that means x is slightly greater than 2. I'd have, again, a number close to 2 minus 5. That would be, again, a negative number. Over 3 is positive. And then x minus 2 squared. A number slightly greater than 2, subtract 2. This would be a small positive positive number squared. And if I square a small positive number, it's still a small positive number. And so this again goes to negative infinity. And so what I can see from this is that the graph approaches negative infinity on either side of its vertical asymptote. And so graphically, what I would expect to see is at x equals 2, I expect a vertical asymptote still, but on both sides, it should go to negative infinity. Let's go ahead and verify this one. X minus 5 over 3x squared minus 12x plus 12. Let me graph that. So x minus 5 over 3x squared minus 12x minus 12. Oh, plus 12. There we go. Like that, then that graph didn't look right. Okay, 3x squared minus 12x plus 12. And what I can see here again is that at x equals 2, I see the vertical asymptote, and I see on either side of the curve approaching negative infinity. Let's take a look at a function that involves some trigonometry. So here we're asked to describe the behavior of the function 3 over cosine x plus 1 at its vertical asymptotes. All right, and again, first we would want to think, well, where are our causes of concern? And so here we would have, where is the cosine x plus 1 equal to 0? That's going to cause us some concern. And so that means then that cosine x equals negative 1. And then remembering from trigonometry, when can the cosine equal negative 1? So there's many places where that can happen. We could have at x equals pi, 3 pi, 5 pi. We could have had negative pi, negative 3 pi, negative 5 pi. All right, so negative odd pi values is what's going to cause some concerns. All right, so let's think about what happens here. It might be helpful to think of the cosine curve if you've forgotten it. The cosine curve does this roughly. There's 0 to 2 pi, not 20. 2 pi. And there's pi. And there's the value 1 and negative 1. All right, so let's think of the limit. Let's just concern ourselves with one of the points when x equals pi. Limit with x approaching pi from the left of the function. And the limit with x approaching pi from the right of the function. All right, so the numerator's 3. All right, that's a positive value. Now, what happens in the denominator? As x approaches pi from the left, the output is approaching negative 1, and it's going to be slightly less than negative 1. All right, as x approaches pi from the left, the output, the cosine, is a little bit greater than negative 1, right? It's slightly greater than negative 1. So if I take that output from the cosine function, that number is slightly greater than negative 1, and I add 1 to it, all right, so again, maybe we're talking about a number like negative 0.999 here, and I add 1 to it, that's going to give me a small positive number, and so that would go to infinity. Similarly, if I'm approaching pi from the right, my output is still the same, or roughly the same. It's still like a negative 0.999, and then adding 1 would give me a small positive number in the denominator. And so this would again give me infinity. And so then what's going to happen here is that at least at pi, I know that for the graph of this function, at pi, I'm expecting this on the curve. And since the behavior of the cosine function at 3 pi is similar, and at 5 pi is similar, I expect a similar behavior at every one of the vertical asymptotes. Let's go ahead and take a look at this graph on Desmos. All right, so the graph is 3 over cosine x plus 1. All right, and here I see a vertical asymptote, and I'm guessing it's about at 3.14. Right, looks to be at about pi. And I see the similar feature here at negative pi, and it's tough to see, but 3 pi is going to be somewhere near 9. And again, I see a vertical asymptote here where it's approximately 3 pi. So this seems to be good evidence that my analytical work was correct. All right, let's look at one more situation. And this is one that you should be aware of. You should know this from algebra already. Describe the behavior of the function natural log x at its vertical asymptotes. So maybe you can think of this one on your own before I do it. All right, so if you remember the natural log function, we can't really analyze this one with algebra. It's just, we have to know this one. We know that the natural log function looks roughly like this, where this is the point 1, 0. Now I know that the domain of the natural log function is 0 to infinity, 0 in parentheses. Remember, I cannot find the natural log of 0. All right, and so really there's only one limit that I can really consider. The limit with x approaching 0 from the right. I can't approach 0 from the left because that's not in the domain of the function. The limit as x approaches 0 on the right of the natural log function is negative infinity. All right, so that's one that we want to be aware of. All right, so I'm going to stop this video here now that we've had some idea of limits where the output is infinite. And then I'm going to have a second video where we will talk about what happens if we are finding a limit as x approaches an infinite value. All right, so I'll see you then.